Good morning, students. Welcome to the class on carbon-13 NMR spectroscopy. We were discussing about the coupling of carbon with deuterium. Similarly, we will also have coupling between carbon and fluorine. Fluorine, whose nuclear spin quantum number is half, it will couple with carbon signals. According to the n+1 formula, we can expect multiplets. Of course, hydrogen, oxygen, chlorine, and bromine, they don't, their spins don't interact with the carbon, so we don't see any multiplicity arising from the coupling between proton carbon or oxygen carbon or chlorine carbon or bromine carbon. So the decoupler will eliminate these couplings, so we don't see any carbon hydrogen or carbon oxygen couplings. But under the similar conditions, we will observe carbon fluorine coupling. Though decoupler is on, but carbon fluorine coupling will occur. Like carbon deuterium coupling, carbon fluorine coupling will also expected in carbon-13 NMR spectrum. Now look at this example. Fluoro tribromo fluoromethane. Because we have only one carbon, we can expect only one signal in the C13 NMR spectrum. Here, the C13 NMR spectrum, at 0 we will have TMS carbons, at 77 we will have CDCl3 triplet peak, and the carbon from this tribromofluoromethane is observed at 46.32 ppm, where we get a doublet with a coupling constant, one bond coupling constant 370 Hz. So the coupling constant is very high in case of carbon fluorine coupling. Because it is having a large coupling constant value, though it is a doublet, we see individual peaks in the doublet. Okay, it is a doublet. In the trifluoroethanol, when we look at the carbon-13 spectrum, the carbon-13 spectrum of this compound gives a quartet at around 125 ppm, a triplet at 77 ppm, and a quartet at 62 ppm. This spectrum is this is proton coupled carbon-13, proton coupled carbon-13 NMR. Here the values of these peaks were 9803.9, 9525.5, 9247.1, and the last peak is 8968.8. So these values represent these peaks. Now from this data, we can clearly say that this compound will give two peaks in the carbon-13 NMR spectrum. One is for this CH2, one is for the CF3. In the proton decoupled spectra, we will expect a singlet for this, but in a proton coupled spectra, this is not proton coupled. This quartet is resulting from the coupling between the fluorine of this carbon and with this carbon. This is a one bond coupling. This is a two bond coupling. So that is why here we have large J value. Here we have small J value. So the fluorines, they are splitting the signal from this carbon. They are also splitting the signal from this carbon. So that is why we are getting, according to the n+1 rule, 3+1, we are getting a quartet here. Similarly, here also we are getting a quartet. But because it is a one bond coupling, that means fluorines are directly present on this carbon, we will have large coupling constant value. Generally, this coupling constant is 278 Hz, whereas this two bond coupling constant is 35 Hz. So with fluorine, one bond coupling is possible, two bond coupling is also possible. Similarly, we also observe carbon phosphorus coupling. We also observe carbon phosphorus coupling. Carbon with its mass number 31 has a nuclear spin quantum number of half. So we can use n+1 rule to predict the multiplicity of carbon signals. For example, take this compound, 4 methyl groups and phosphorus. Of course, they are equivalent carbon, so we will get only one signal in the carbon-13 NMR spectra. But phosphorus will couple with this carbon, so the single signal will be split into a doublet based on the n+1 rule. N means number of phosphorus atoms, because we have one phosphorus, 1 + 1, 2, doublet. So this doublet is observed at delta 12 ppm in carbon-13 with a coupling constant value of 56.1 Hz. 56.1 Hz. I'll give you one more example. In this molecule, we can expect two signals, one for this carbon, one for this carbon. Since these two are equivalent, we will get only one signal. Here, this carbon is directly present on phosphorus, so we can have a large coupling constant value, whereas this carbon is two bond away. So it is a one bond coupling, this is two bond coupling, so we expect small coupling constant. The carbon which is present on oxygen will give a doublet like this, whereas the carbon which is directly attached to phosphorus will give a doublet like this. Because it is a one bond coupling, it gives large coupling constant of around 144 Hz, whereas it is a two bond coupling, it gives a small coupling constant value of 6 Hz. It is observed at 52 ppm. It is observed at 10 ppm. Now let me add one more point. The coupling constant here is 144 Hz, whereas the coupling constant in this molecule it is 56 Hz. When we want to compare them, in case of fluorine, its coupling constant value is almost 300 Hz. But here we can see a large difference, right? So what we can say is the coupling constant value of phosphorus with carbon depends on hybridization of the phosphorus. When we change the hybridization state of phosphorus, the coupling constant will also change. So with increase in hybridization, we get a large coupling constant value. So the coupling constant value of copper and phosphorus depends on the hybridization of phosphorus. When we were given frequencies, then in order to find out the J value, you just take the difference between these two peaks. Okay, just take the difference between these two peaks, that will give a coupling constant in hertz directly. But if we were given delta values for this peak and this peak, we need to subtract, we need to take the difference in delta value multiplied by instrument frequency. So then we will get the coupling constant in hertz. Okay, so if you are given frequencies directly like this, just take the difference between any two peaks, we will get the J value. But if we were given delta values, take the difference, then multiply the delta value with instrument frequency, so that we will get the coupling constant value. I'll give some proton NMR values and carbon 13 values, their multiplets for some deuterated solvents. For acetonitrile, we observe two carbon 13 NMR signals, one at 1.3 ppm, another one at 118.3 ppm. Because we have three deuterium atoms on carbon, we expect a multiplicity of 7, whereas this carbon, it doesn't have any deuterium, so we expect a singlet. So multiplicity only 1, a singlet. In the proton NMR also, due to the rapid exchange of deuterium with protons present in the solution, we do expect a signal at 1.93 ppm with a multiplet quintet. In benzene D6, because it is a symmetrical molecule, we get only one peak. We get only one carbon signal in C13 NMR, that is at 128 ppm. Because we have one deuterium on the carbon, according to the 2ni plus 1 rule, we get a triplet. Multiplicity is triplet. Due to the rapid exchange of deuterium with protons present in the solution, we also get a proton NMR signal for deuterated benzene at 7.15 ppm with a broad singlet. Dioxane D8, where all the hydrogens are exchanged with the deuterium, we expect a signal at 66.5 ppm with a multiplet of quintet because we have two deuterium atoms. Methanol D4 where CD3 OD, we get a carbon 13 NMR signal of 49 ppm and a multiplet of 7 peaks. For proton NMR, deuterated methanol will give a singlet at 4.84 ppm, one multiplet singlet, and another peak at 3.30 ppm with a quintet. Now we will discuss a brief discussion about nuclear Overhauser enhancement NOE effect. I'll explain this with an example. N-propanol, when we take the proton coupled carbon 13, and proton decoupled carbon 13, the difference is, when we take proton couple, we will expect 3 signals because 3 are there, 3 plus 1 quartet, triplet and triplet. So we get a spectrum of triplet, it is supposed to give quartet, but quartet and triplet, sorry. But the same molecule, when it is taken with proton decoupled spectrum, what do we expect? In a decoupled spectrum, we have one more RF source. Using that RF source, what we will do, we will irradiate all proton sources with high energy. So when we pass resonance energy required for resonance of protons, so all the protons will be saturated, so we don't expect any coupling coupling for the proton. So proton, when we irradiate proton with high energy, it will not couple with this. So what we will get singlets in the spectrum, right? When we get the singlets, how they look like? They look like this. Why? See, this proton coupled spectrum, the intensities of the peaks are very small, whereas the proton decoupled C13 NMR, the peaks are having very high intensity. This is due to nuclear Overhauser enhancement. The enhancement is greater for CH3 than CH2, which in turn greater than CH, and we don't observe any enhancement for carbon. So the nuclear war has an enhancement effect. It may be homonuclear or heteronuclear. That means this effect can be observed between carbon-carbon or carbon-hydrogen or any atoms. It may be heteroatom also. When we irradiate protons with very high energy with a decoupler, so the second RF source is called decoupler. So when we irradiate the protons with a decoupler, they will undergo saturation, so they don't couple with that. But what happens? The intensities of, that means the intensities of proton peaks, they will add to carbon signals. Due to that addition, the intensities of the carbon signals will increase. So the enhancement in the carbon signals, it depends on the number of protons or number of atoms attached to the carbon. If we have 3 hydrogens, the enhancement will be larger. If we have 2 hydrogens, the enhancement will be lesser compared to 3 hydrogens, something like this. We can calculate the extent of NOE effect. The maximum enhancement is given by NOE maximum is equal to half of gamma irradiated by gamma observed. For example, in this case, we are irradiating protons and we are observing the carbon signals. So we need to take gamma of protons by gamma of carbons. As we know, gamma of protons is 4 times larger than gamma. So gamma of carbon, we get 4 here. So NOE maximum for protons is 2. NOE maximum for protons is 2, or nothing but it is called as 200%. It is called 200% for protons. So when we irradiate protons and we observe carbon signal, we observe 200% enhancement. Therefore, total signal, total intensity of the signal, so total predicted enhancement, total predicted enhancement is nothing but 1 plus NOE maximum. 1 plus NOE maximum. It is mainly due to the cross polarization of the spins of the atoms involved. So I am not going detailed discussion about the NOE. NOE effect can be a great help in carbon 13. As we have discussed for the previous case, proton coupled carbon signals were less intense, whereas proton decoupled carbon signals were of very high intense. For example, the same concept can be applied to this. When we irradiate protons, not only this carbon signal, the carbons which are nearer to this proton, their signal will also increase. So what we will do, we will irradiate, when we irradiate this that means when we irradiate protons with RF frequency, then the carbons which are nearer to this proton, they will also improve their signal. This is cis related to this proton. This methyl is trans related. So we expect NOE maximum, NOE effect for this. So out of these two, as I said, for DMF, for amides, we get 2 peaks because the carbon nitrogen bond rotation is restricted in DMF. For amides, we get 2 signals for these two. In order to identify which methyl is cis2 hydrogen, which methyl is trans to proton. NOE effect will be useful. Because it is syn to methyl, we expect NOE maximum. This is observed at 36.2 ppm, and this is anti. So we don't expect NOE for this. So no NOE. So when we want to identify these two in the spectrum, they will give two signals, but the highest intensity methyl group will be this one. The lowest intensity will be this one. Why? Because of this proton, we are observing NOE for this methyl, whereas we are not observing NOE from this. Of course, this is a methyl, this is a methyl. Because of the proton decoupling, we expect same NOE for these two methyls. But this is an additional factor, additional NOE to this methyl only. But this methyl, it is anti-related, so we don't observe any NOE maximum signal enhancement for this methyl. So this is how we can identify the stereochemistry of the compounds. Not only this methyl, any groups which are syn to hydrogen, we will expect NOE enhancement. So anti groups, we don't expect any NOE enhancement.